Hi, welcome. So let's go to our presentation. So open a Chrome tab or a Firefox tab and go to the following link, which is www.lucadistasioengineering.com/project 2016 number 9. And if we press enter, we're gonna view in a few moments the presentation. There we go. So today we are gonna talk about applied control theory, and in particular we are gonna dive deep into the paper Bending Moment-Based Force Control of Flexible Arm Under Gravity. So first things first, how to navigate these slides, which I remark are freely available on the internet at the link that you can see here in the Chrome bar. So if you press Ask, you can have an overview of the slides, while you can navigate through each slide using the arrows here in the bottom right corner or using the arrows of your keyboard. You can also, in a simpler way, use the space bar to go to the next slide. The organization is pretty simple. Along the horizontal direction, so left and right, you go through the sections, while along the vertical direction, so up and down, you navigate inside each section. So well, what we're gonna do, we're gonna present the model and go through all the derivation in the paper, and the problem is the design of a closed loop system for the control of a flexible robotic arm. References: this is not the orthodox way to present the references. They should be at the end, but I prefer to put them at the beginning to highlight on which papers we are gonna work. So 3 papers in particular. So the first one, which is the paper which is the main subject of our presentation, plus 2 other papers which are helpful in understanding the derivation, the problem, and the assumption. In particular, the second one, which is pretty important, and many of the derivation are in this second paper here. So let's proceed now. Why would we want to model a flexible robotic arm? So basically, what's the rationale behind this paper and this presentation? Well, it can be summarized in just one picture. So this is quite important to remember later on when we're gonna derive our model. And so our reference in real life are robotical surgical arms, so which are motor controlled, they can rotate, in particular, are flexible, and they have to touch surfaces. Okay, so in this case they are gonna touch the table in a very simple manner. They can touch, in principle, very different surfaces, but the important thing is that they're gonna touch surfaces, and they need to do that with precision, with small to no vibration at all, and with extreme precision in the position. So let's start with the first section, which is the formulation of the model. So we model our arm as a slender flexible beam clamped to a vertical shaft in the origin O. The environmental interaction of the arm, so the presence of object and the external room, is modeled by the presence of an object here on the right of our diagram, which interacts with our arm by simple contact. Now, to model the presence of a hand, of a robotic hand, or some kind of manipulator at the end of the arm, we add a mass, a concentrated mass, M. We are gonna later on go through the symbols. And the system is controlled by a force U of T acting on the tip mass at the end of the arm. And furthermore, gravity G is present. So, assumption. We are gonna work in 2D. The beam is assumed to be slender, and to satisfy the Euler-Bernoulli beam theory, small angles and small displacements are assumed. So we are assumed to work in a situation of small oscillation around the equilibrium and the link between the arm and the shaft, so this point here, is assumed to be perfectly rigid and smooth, and furthermore no friction is present between the object and the tip mass. So, let's start with our variables and parameters. First of all, the reference frames. We have two reference frames, one inertial one, in particular a fixed one, which is denoted by ij. So I and j are the unique vector or versors of the axis, while x and y are the coordinates. And then we have a second reference system denoted by x, y, I, j in small caps, which is a dragged reference system which rotates rigidly with the shaft. Now, system properties. We consider the following properties. For the beam, linear density ρ, length L, and flexural rigidity EI. For the end tip, mass M, concentrated mass M. For the motor, inertia, moment of inertia J, and applied torque tau M. For the environment, let's say G, the acceleration of gravity at sea level. So in absolute value, G is equal to 9.81 meters per second squared. In absolute value, because the sign depends on the reference. In this case, G as a vector is exactly our minus G in absolute value times J. So let's move to the independent variables, which are theta of t, the angle of rotation of the motor of the shaft, this is theta, and w of x t, which is exactly this distance here. So is the vertical displacement of the beam with respect to the rotated horizontal axis, x, small x. Now pay attention that here in the diagram, W appears to be negative, or in some, or let's say defined in the negative direction. It appears to be defined in this direction. Actually, W is defined positive, so W positive is along the positive y's, and this is just a matter of representation, so we can just erase it, and W is just defined along the positive y direction. The control variable is just 1, and that's u of t applied here at the end of the flexible arm where the mass tip is located. So let's go on and let's introduce a few features of the kinematics of this problem. So let's introduce the matrix R, which defines the transformation from the inertial reference frame, capital Q, to the drag reference frame, so small q. So if we have a vector here, we can call it capital Q, and that's defined in the fixed reference frame x and y, and that's Q. But then we can consider it with respect to the drag reference frame as small q with components small x and small y. Now the relationship between the two is defined by matrix R, and to derive the matrix actually is pretty simple. We just have to write down, if we write down big X with respect to small x and small y, we have, if we draw the triangles, so this is theta, this is the complement to 90 degrees of theta, so theta is here, theta is also here and here. So big X is equal small x times the cosine of theta minus, we see minus y times the sine of theta. Then big Y is equal, if you see x sine theta positive plus y cos theta. So if we gather in a vector big X and big Y, we'll get exactly, if you see, we'll get here r minus 1 of small x and small y. Okay, so cosine minus sine here and here, sine and cosine here and here. So in this way we can derive r minus 1, and just by inversion we can get r. So the matrix here is orthogonal, which means that the determinant of r is equal either plus or minus 1, plus in this case, and so the inversion is just a transposition. So r minus 1 is equal r